Thank you for coming to this presentation entitled, How is Time Frequency Space Modulation Related to Short-Time Fourier Signaling? This is part of Globecom, IEEE Globecom 2021, and my name is Akbar Saeed. So let's review the introduction, here's the introduction of the talk. The motivation for it is that orthogonal time frequency space modulation was introduced in 2017 as a scheme for high Doppler scenarios. It is very intimately related to orthogonal short-time Fourier signaling introduced by Saeed's group in 2004. However, while a lot of papers have built on OTFS, some much needed comparison between the two schemes is missing. So that's what this paper is aimed at, to look at them, and we show that they are unitarily equivalent in the digital domain. That's what this schematic shows. We'll go over it more. However, OSTF defines the analog digital interface to the doubly dispersive channel. In fact, the OSTF basis functions serve as approximate channel eigenfunctions. So we introduced a sample modeling framework for comparing all time frequency modulation schemes, including the two talking about here, and we revisit the results and we show that the constant diagonal property of OTFS, and it has a surprising consequence that the capacity and probability of error performance is in the opposite directions in the two schemes. And then we also show that OSTF requires significantly less channel state information due to its eigennature. So let's review orthogonal signaling in time frequency space, or time and frequency. So we have an n-dimensional information packet with duration t and bandwidth w. Dimension is n equals tw. And these dimensions can easily be, they're related to the critical sampling in time, which is 1 over the bandwidth, critical sampling in frequency, which is 1 over the duration. And if you do these samples over time or frequency, you get tw. And we also related to these nt-nf, which is the multiplexing parameters. So how we use these dimensions depends on the pulse waveform. So here is one extreme time multiplexing. So this is frequency, bandwidth, duration. And in time multiplexing, you use narrow time pulses of the same duration as the critical sampling period, and you multiplex the symbols in time. So that's what's shown here, and you use nt equals n time symbols. The other extreme is frequency multiplexing, or OFDM, where you multiplex the symbols over narrow frequency bands of the same width as the critical sampling in frequency, and you have n of them which span the entire bandwidth. But the more general case is time frequency signaling, where you use an underlying basis function or waveform of duration t naught and approximate bandwidth f naught, and the product is equal to 1, and you translate them over time through nt shifts and over frequency with nf shifts. And so you're now modulating onto time and frequency shifted version of these basis functions. That's short time Fourier signaling, and these two are the extremes of that. Now, the pulse scale is an important thing. We are considering communication over doubly dispersive channels, which consist of propagation over multiple paths, each with its own delay and Doppler shift and path gain. This is the time varying frequency response. So the optimal pulse scale depends on the delay and Doppler spreads. And as shown in our 2004 paper, the ratio should be proportional to the ratio of the delay and Doppler spreads. And so that gives you these optimum values. And that's what's shown here. This is a highly dispersive channel. This is T naught. This is F naught. This is the OTDM extreme. This is OFDM extreme. And this is the optimal pulse scale. And here's the effective channel between the n dimensions for OSTF and OFDM. It may not be visible, but there's a lot more mass distributed around the diagonal as well. Not all concentrated on diagonal, whereas it's more concentrated on the diagonal in OSTF. We'll see that later too. So how is OSTF related to OFDS? Well, it's digitally unitarily equivalent. And so that's what's shown here. There's a channel, transmit signal S of t, receive signal R of t, and if in STF you modulate onto the STF basis function, the time frequency shifted versions of that basic pulse, and so modulate them at the transmitter onto these pulses, the STF symbols, goes to the channel with noise, and at the receiver you project onto those basis functions, since this matrix USTF is a unitary matrix. In OTFS, what's happening is it's actually the same modulation scheme. The symbols are different, and they are related to the STF symbols through a two-dimensional Fourier transform or symplectic finite Fourier transform, SFFT. And that's what's shown here. If you look at the symbol matrices, you're hitting them with the left and right with the unitary TFT matrices. And so that's these extra unitary matrices. If you sandwich OSTF system between those, you get the OTFS system. And this is the relationship between the two unitary transforms for the two modulation schemes. So now we develop a sample matrix system model to analyze all different time frequency modulation schemes. So we take the input-output relationship, you discretize it, critical sampling and then time and frequency. You get an n by n sample system. This is the n-dimensional vector corresponding to the samples of the received signal. This is the n-dimensional vector corresponding to the transmitted signal samples, and this is samples of the white noise. And this is the effective matrix, H tilde, which is just a sample version of the time varying frequency response with this modulation factor. And UN conjugate transpose is basically the DFT transform from mapping S to S of F. Now, if you look at the short-time Fourier signaling system, you take these symbols, put them into a vector. The transmitted signal is modulating these symbols over the STF matrix, and they go back and forth since they're unitary. At the receiver, you project onto the basis function, and this is a composite matrix, the original matrix sandwiched between the USTF transform. UTFS, and these are the localized time frequency basis functions. UTFS, you can see that this spreads the information over all of the time frequency plane. And again, you modulate onto the TFS basis functions, if you will, or transform, and at the receiver, you project onto them. And what you can see is that this is the overall composite relationship, where it is HSTF sandwiched between these symplectic Fourier transform matrices, which is essentially a Kronecker product of an NF-dimensional DFT matrix and an NT-dimensional. And this is a relationship between the two. So that again shows a unitary equivalence and also a new model. Now, even though OSTF basis functions are as approximate eigenfunctions, there's still some interference between them. So this is a unified system model. These H, Y, and X correspond to STF, TFS, or OFDM, we'll see. And we're going to use linear MMSE interference suppression, but these matrices could take STF, and these are the transmitted symbols that receive demodulator outputs, or HTFS, or OFDM is a special case of STF by putting NF equals N and NT equals 1. And the LMMSE matrix then is just an n by n matrix to suppress the interference. And the matrix is given by R inverse H, where R is a covariance matrix of the demodulator outputs. There are two key system matrices, H and HC. HC is the composite matrix, including the MMSE filter. And in addition to probability of error, we consider three other performance metrics. The channel diagonality metric, which basically is the ratio of the power in the diagonals to the total power in the channel matrix. So we expect it to be the highest for STF since it's close to eigenfunctions. Signal to interference noise ratio in each dimension, which is basically the ratio of the signal power in that dimension divided by the interference from the other dimensions to this dimension plus noise. And then the spectral efficiency can be gotten from these SI and R by summing them over the n channel and divided by n. So this in bits per seconds per hertz. So let's look at some numerical results. So basic system parameters are 4 gigahertz carrier frequency, 15 megahertz bandwidth. The signal size dimensions are about 1200. T is about 80 microseconds. This is our matrix system model that we have reviewed. We consider 4 QAM, and we consider 5 different modulation schemes, STF, TFS, and then since TFS is related to STF through this unitary transform, we also look at another version of STF where we replace the SFFT with the arbitrary unitary transform. And as we'll see, the perform almost identically. And this has been shown by some other folks too. Then OFDM also, where NF equals N in the OSTF matrix, and a baseline eigen-based system which communicates over the singular vectors at the transmitter and receiver. And this is the diagonal effective channel matrix so that there's no interference. And we consider two different scenarios. We have 30 pads. In one case, the delay spread is moderately dispersive channel. The delay spread is 300 nanoseconds and Doppler spread about 2 kilohertz. In a highly dispersive channel, we consider 700 nanosecond delay spread and about a 10 kilohertz Doppler shift. And this is the picture of this is a time varying frequency response function. This is a new delay Doppler function with a two-dimensional Fourier transform of this. And these are the normalized delay Doppler shifts. So here's the first set of results, OSTF versus OTFS, the channel behavior. So on top panel row is moderately dispersive. On the bottom, it's highly dispersive. This is just transmit symbol, receive signal, and this signals at the output of the MMSE. You can see the QAM constellation. The middle panel shows, the top one shows the diagonal terms of H, the original matrix, OSTF versus OTFS. Notice that OTFS is almost constant, whereas STF shows wild fluctuation because of multipath randomness, and there's quite a bit of loss in SNR or the value. And when you do MMSE filtering, this gap gets much lesser between OSTF and TFS, but still it's flat. If you look at the average SINR at two different operating SNRs, what we see is that the average SINR over the channels is much higher, about 3 dB higher or so compared to OTFS, and that gap stays even after you apply the MMSE filter. This is SINR, obviously, and even if you increase the SNR, and so you can see there's about 3 or 4 dB gap here. And if you look at instantaneous SNR, that is again lower, but flat versus wildly varying. And but the average SNR takes a big loss. And that's also shown in the diagonality metric, where OSTF and eigen are way on top because they have the best diagonality metric. And then OFDM is close there too. And then this is OTFS as well as OSTF-U, the generalized one. And they have a very poor diagonal metric without MMSE. And then when you apply the MMSE matrix, their metric gets better. And in the highly dispersive channel, the situations get more accentuated. So here we do probably a error versus capacity comparison with the full channel state information. So for MMSE filter, we use the entire channel state information. What we see is that the best performances capacity is OSTF and eigen. This is SNR per dimension and capacity. Whereas OFDM is pretty close to, since it's moderately dispersive, but OSTF-U and OTFS are slightly below. In probability of error, we see the opposite behavior. OTFS or OSTF-U give much better performance. OFDM is next, and then eigen and OSTF have in some ways the worst probability of error performance. And in highly dispersive channel, this gap increases. OFDM also separates from OSTF, and the probability of error comes somewhere in the middle too. And overall, it's going down because there's more diversity in the system. So since OSTF is approximately diagonal, most of you know that most of the power is going to be in the diagonal elements. This is the MMSE matrix for OSTF. So what we say is, okay, how about if we just use the diagonal channel state information to design our matrix? So you can see that in OTFS, you're going to be losing a lot of non-diagonal information. Same with OFDM, even though it's more concentrated. So this is the diagonal entries. OTFS is lower value, constant. OFD is varying around. And then blue is the OSTF entries, diagonal entries. And if you look at the diagonal system performance, what you find is that the roles reverse. OSTF and eigen are still the best. OFDM is worse. And OTFS takes a big hit because its information is spread all over the dimensions. And in probability of error, it also goes the opposite. OTFS is now the worst, then OFDM, and then STF, and then eigen. And that, of course, performance doesn't change exactly the same. And we notice that if we add more diagonal, this performance will get even closer. So to conclude, what we've shown is OTFS and OSTF are unitary equivalent in the digital domain. However, the crucial analog digital interface is defined by OSTF basis functions. We have proposed a sample modeling framework that enables unified analysis, and we have shown the constant diagonal property, but it also comes with a lot of SNR, SINR. And comparison in full CSI and diagonal CSI highlights the eigennature of OSTF. It opens many new directions, for example, coding techniques that exploit channel structure, but that's for another day. So I'll stop here and thank you again.